Yeah, you're back. Well, as promised, let's do example 3. So the Golden Gate Bridge, I'm from San Francisco. Bit of personal trivia about me, yay. Spans San Francisco Bay. It is 746-foot tall towers. There are 2 of them. They are 4,200 feet apart. And there are 2 enormous cables. They are quite thick, 3 feet in diameter. So the 90-foot wide roadway is 220 feet above the water, and the cables are shaped as a parabola. This is actually not quite true, but for the sake of this problem, let's just simplify it. Okay, they touch the road surface at the center of the bridge. That's more or less true. So find the height of the cable above the road at a distance of 1,500 feet from the center. This looks totally impossible. We don't even have any functions at play. We're given a whole bunch of numbers. It's rather intimidating, but trust me, we'll be able to work through it, okay? There are 746-foot tall towers. They are 4,200 feet apart. So the first thing I draw is I have a tower and a tower. They are 746 feet tall. Okay, and the distance between them is 4,200 feet. So then once I have these towers, there is a parabola that joins, oops, sorry. Oh, well, here's a picture. It's better than mine anyway. So the parabola is going to come down from the towers and touch the road. Okay, so that's what that's supposed to represent. We have to start putting coordinates down, and we've just decided this intersection of the road with the cables, let's go ahead and call that the origin. Okay. It happens 220 feet above the water, and the towers were a total of 726 feet tall. So what's the height above the roadway? 526 feet. Okay. If there was 4,200 feet between the 2 towers, then there's 2,100 feet left and 2,100 feet right, because we know a parabola is nice and symmetric across its vertex. Okay, and we were told the road touches the parabola at its vertex. So, using the information we were given, okay, the road is 220 feet above the water, but the towers are 726 feet tall, 776, sorry, feet tall. That gives me, I'm saying the wrong words, it was 746 feet tall. That gives me that the height of the tower is 526 feet above the road. We were also told that the distance between the 2 towers is 4,200 feet. So since this is exactly the vertex, it's exactly symmetric across both sides, we're going to get 2,100 feet this way and 2,100 feet this way. So we can label these 2 points as plus or minus 2,100, comma, 526. And we know that we've labeled the vertex to be the origin. Okay, so now we have a parabola where we know the vertex and we know one other point, and therefore we can find an equation for this parabola. So we have a vertex at 0, 0, and we have a couple of other points on the graph. Okay. So then we can find the value of A in this upward opening parabola. This is already in vertex form, I want to stress. So vertex form, remember, was a x minus h squared plus k, but our vertex is the origin, so it's 0, 0. So this can be ignored and this can be ignored, and we get exactly ax squared. The only thing we need to determine is the value of a. So let's take that other point, 526, 2,100. So if we plug in, sorry, 2,100, 526. So if I plug in 2,100 for x, I'm going to get out 526 for y, which means a can be solved to be 526 over 2,100 squared. Notice this is not the same thing as 526 over 2,100 squared. A lot of people would make this mistake punching it into their calculator or something. So therefore, this is the equation of the parabola. We were then asked, when x is 1,500, what's the height? Now, leaving it in this expression rather than trying to simplify this as some very small number actually makes our lives a little easier, because notice I end up with 1,500 squared, because x is being squared, over 2,100 squared. So off on the right, okay, so 1,500 squared over 2,100 squared. This is the same as 1500 over 2100 squared, and now I can cancel these out. I can also even cancel out a 3. This is just 5 over 7 squared, or 25 over 49. So this all simplifies to just be 25 over 49. Okay, but then y just gives me a value of 268.4 feet. That's fine. So 1,500 feet away from the vertex, the cable is 268.4 feet from the road. I want to go back to the picture just to point something out. I mentioned that the cable doesn't quite hang as a parabola. And that's not because I am some font of information about the Golden Gate Bridge. It's a mathematical fact. If you hang a cable between 2 points, the shape that it generates, it looks kind of like a parabola, but it's something different. It's actually called a hyperbola. It's not quite a parabola. A hanging cable always forms the shape of a hyperbola, not a parabola. It's a different equation that just you would solve with different techniques. It visually looks pretty similar to a parabola, which is why at this point the book has said, sure, let's just throw this example at them and pretend it's a parabola. Anyway, we'll go on. Okay. Now let's suppose I have a chart of data. Can we fit this to a quadratic function to try to use the model and like predict other stuff? So here's data. If I have the age of various customers, I can look at how much they have spent, E. So 21.4-year-old person has spent $34.4 thousand. Just annually, this is how much they spend. And it looks like as your age goes up, your expenditures go up until a certain point where they start going down again. Okay, so this is not linear. It goes up, but then it comes back down. So can you draw a scatter plot? Sorry, I'll go back just so you can have a chance. Copy this data down, and then we'll move on. I'll just give you a moment, pause here to copy this. Okay, so hopefully we copied that down. So draw a scatter plot where you have age, comma, expenditures. Comment on the type of relation, just asking is it linear or quadratic or something else. Use a graphing utility to find the quadratic function of best fit. Remember, in any utility, best fit is usually regression, but we're not looking for a linear best fit, we're looking for a quadratic best fit. So you're looking for something called quadratic regression. Then use the model found to approximate the age at which the expenditure is largest. Use that model to approximate what that biggest expenditure is, and then graph it. Okay, so I'll pause here. Okay, so here's the scatter plot you'd get. It does look kind of like a parabola, but not exactly. Okay, it is opening down, it's concave down, which does match the question asking, can you find the biggest possible or the maximum expenditure? Okay, so using quadratic regression, it tells you here's your A, B, and C, and most utilities, for example, the TI-84 one, will actually specify, it doesn't just give you A, B, and C, it reminds you what the function should look like, ax squared plus bx plus c. Okay, so there is our quadratic model. How am I going to find what age has the highest expenditure and what that expenditure is? Well, that's going to be the vertex. Negative b over 2a gives me the age of greatest expenditures. And we just take the b and the a that were given by the calculator, about 49.5 years. And if I were to plug that in, the corresponding expenditure would be about 69.1, and remember that's thousands of dollars. So on average, a 49.5-year-old is spending $69.1 thousand per year. Okay. Data for these problems, by the way, is generally taken from some sort of real-world thing, sometimes simplified so that the math works out. So why do you think, starting at age 21, expenditure goes up until about the time you hit 50 years old, and then it starts coming down? On average, this is not like universal for every single person, but on average across the population, generally you have kids and you have to spend money on them. And then at a certain point, they start making their own money, and then your expenditures start going down. Okay. So here is a graph of that function. It's a fairly good fit. Could you find this function by hand? Yes, using calculus, it's a fairly unpleasant process. the theory behind it isn't so bad, but actually working it out by hand would be kind of a nightmare. We generally just let computers do it. Okay, so that's the end of section 3.4, building models from data and using them, and using calculators to work with them. So come on back for section 3.5.